Dear colleagues, it is my great pleasure to present here our recent results on our collaborative work between the University of Southampton, the University of Sheffield, Skoltech, on the nonlinear dynamics of the energy landscape in Frenkel exciton-polariton condensates. Exciton-polaritons are quasi-particles in solid-state systems that originate from strong light-matter interaction between standing wave, cavity photon, and exciton in the semiconductor material. And if the interaction is strong enough, so stronger than the cavity decay rate and stronger than the dephasing, exciton dephasing time rate, therefore one can diagonalize this kind of Hamiltonian, general Hamiltonian of light-matter interaction, and end up with the polariton states, which are coherent superposition state between exciton and photon. The beauty of exciton-polariton system is that polaritons consist of photon part, and normally this photon part is substantial, and you can through the just through the measuring light leaking out from the cavity, we can easily therefore characterize the whole state inside the cavity, what's going on inside the cavity, and we can measure everything basically: energy, momentum distributions, coherence, and basically all the information can be easily accessed, spin and spin state and everything basically. Another important thing that exciton-polaritons are bosons, therefore being bosons they can undergo BSC phase transition, which is from the standard theory of BSC correspond to some critical temperature normally. So below this critical temperature, usually the BSC is happen. And according to the standard theory, we know that the critical temperature is inversely proportional to the effective mass. And this is the place where another advantage of the polariton systems comes. Because it is partially photon, therefore we can rely on a very small effective mass of the polaritons. Therefore, having a small effective mass, we can also get the BSC phase transition at quite high temperatures, at a much elevated temperature with respect to atomic gases and excitons, as you can see here. So, and indeed, Bose-Einstein condensation of exciton-polaritons has been reported experimentally in 2006 for the first time, where it was achieved at 19K, and then later on it has been done even at room temperature with usage of organic materials instead of conventional semiconductor material inside the microcavity. But there is a very important feature of our systems is that it is not only the photonic component is present, but also a meta component. And the meta component gives rise for interaction in the system. So our Bose gas is not Bose gas is not ideal Bose gas. It is basically interacting Bose gas. This happens because of Coulomb exciton interaction, which is very pronounced in conventional 3-5 systems, and it gives rise for nonlinearity in nonlinear Schrödinger equation for the wave function of the condensates, which can be easily witnessed as the increasing energy of polariton state with respect to polariton density, so-called blueshift. So more polaritons you put into the system, so the higher the energy of the system. So the blue shifts with respect to the unperturbed state, let's say. And this linearity is actually and this linearity is a stepping stone for lots of applications and lots of interesting physics, for instance. It is widely utilized at the moment to study many body problems in solid-state physics on the polariton lattices, imprinted either through the lithography methods or through the optical methods like we do in our lab. And also it is this kind of linearity is the the underlying mechanism for polariton superfluidity have been demonstrated a while ago, and recently there was shown that this polariton linearity could be strong enough to see experimentally blockade effects, polariton blockade effects that put the whole field into the let's say quantum regime of operation. Although it is very well understood what drives linearity in inorganic system in conventional 3-5 semiconductors, it is still quite unclear what's going on in organic microcavities, strongly coupled organic microcavities. They actually quite a nice system because they can support exciton-polaritons at high temperature, at room temperature, even at above room temperature, because organics bear Frenkel excitons that exhibit very high oscillator strengths and very high binding energy. But the dark side, let's say, of the Frenkel excitons is their small effective exciton Bohr radius. Therefore, Coulomb exciton-exciton interaction is not present anymore. But nevertheless, in all the experiments, vast majority of experiments, we observe blueshift phenomena. So with increasing the energy density of polaritons in the system, we see that the energy of polaritons increases as well, as you can see here. So it just increases with the increase in pump power. And in our study, I believe we figure out what's going on because we really study, I think, all possible scenarios that could contribute change of the energy in the polariton system, not only blueshift, just all possible changes of the energy. Of course, we considered polariton-exciton interaction, polariton-polariton interaction. We consider saturation of optical transition for those molecules which are strongly coupled to the microcavity. We also considered some non-trivial contribution which hasn't been considered before, namely saturation of optical transition for those molecules which are weakly coupled with the cavity mode, so-called dark molecules or weakly coupled molecules. And we also considered gain-induced frequency pooling of the lasing mode. I wouldn't tell about that because of the limited, let's say, time scale of the presentation. And also we considered resonant optical intracavity effect, which you can also find in this paper, but I also wouldn't tell more about that. And finally, we considered how does then we investigated how does non-intermolecular energy transfer affect polariton condensation, its spectral and polarization property. Yeah, and we showed that this is actually affect a lot as well. So our material system is the following. It is the lambda-half microcavity, strongly coupled microcavity, the two DBRs basically, and organic material is the following: body pi G1 dye, dispersive polystyrene matrix film, matrix in two different concentration. I will tell a little bit more about that. Yeah, and the feature of this sample is the following. It is grown in wedge-like geometry, such that we can, by changing the position on the sample, we can easily access different detuning, and that allows us to investigate blueshift in the quite large parameter space, and yeah, and draw some reasonable conclusion out of that study. So first of all, I would like to present how does the PL photoluminescence of microcavity looks below threshold. It is just, you can see the very bottom of the low polariton branch, the parabolic-like dispersion, and it is more or less smoothly, the polaritons are smoothly distributed along this dispersion. But once we cross the threshold, all this emission collapse to the very ground state, and the condensation, polariton condensation, accompanied with the jump-like blueshift of the mode. You can see it here clearly. The maximum of emission is actually above the red line, and also it accompanied with the substantial line narrowing, so the coherence in the system is built as well, and superlinear increase of the PL total emission above the threshold. So first we investigate polariton interaction. Is there any contribution from polariton scattering or polariton exciton scattering that we know is present in the standard Gross-Pitayevsky equation for polariton system? We experimentally studied how does the blueshift changes for a single condensate realization changes with respect to the energy of the mode. And then we also, for the whole range, we measured reflectivity maps, and from the reflectivity maps from the anti-crossing of upper and lower polariton range, we extracted for the whole range we extracted Rabi splitting between upper and lower polariton range, and also the detuning between cavity mode and exciton. And using this data, we put them into the standard, very well-known formula for exciton fraction, and therefore we can we found that what the exciton fraction correspond to each energy of the polariton mode, and then from that, so this information allowed us to end up with the dependence of blueshift as a function of exciton fraction. This is very important dependence because it allows us to examine polariton interaction. We can see here that here modulus of x square correspond to exciton fraction, and beta equal 1 correspond to linear blueshift, so-called exciton-polariton and scattering, exciton-polariton interaction, and here polariton term would result in power of 2 in exciton fraction. So we put all this data here, and then we try to fit this with different functions, and the best fit result us with the beta equals 0.7 for the power law of exciton fraction. Therefore, from here we can conclude that it is very unlikely that polariton interactions in general contribute to the process, because one should expect superlinear or at least linear dependence, but not sublinear, of course. Another mechanism which we considered also in great detail is the saturation of optical transition of strongly coupled molecules, so-called bright molecules. So what's going on in here? Once you pump more and more your excitonic material, your organic material, then you basically at some point you start to saturate your ground state absorption. It's just because you have more and more excitation in the system and less amount of molecules in the ground state. That would lead to a quenching of oscillator strengths, and that also converts into the quenching of Rabi splitting, light-matter interaction. So if one put this dependence for the Rabi splitting into the Hamiltonian, let's say, then it is easy to end up with such a dependence for upper and lower polariton branch as a function of density-dependent Rabi splitting. So here the Rabi splitting is not constant anymore, but it is dependent on the number of excitation in the system. Besides bright molecules, there are lots of so-called dark molecules, those molecules which are weakly coupled with the cavity mode. This is always happen because some molecules have wrong direction of their dipole moment with respect to the electromagnetic field. Some molecules are out of resonance because of disordered nature of organic materials. This is very well known, studied in theory by Vladimir Agranovich, Maria Litinskaya, and David Lizzie, for instance, a while ago. And also experimentally in the group of David Lizzie, it was also studied a lot. Yeah, there are many reasons why dark molecules should be present in the system. But since in the vast majority of experiments, researchers apply non-resonant excitation to the system, therefore we excite not only the bright molecules, we excite also dark molecules as well, and we excite them in the same proportion. But unlike bright molecules, dark molecules do not, let's say, directly affect polaritons, but they do it indirectly through the change of refractive index. So once you saturate dark molecules as well, saturate the ground state absorption of dark molecules as well, therefore you affect the effective refractive index of the cavity material, and this refractive index change the energy of the cavity mode, and therefore you effectively change a little bit the tuning of the system, and therefore you also can shift polariton states up or down depending on the refractive index change. If refractive index increases, energy decreases. If the refractive index decreases, energy increases. We carried out rigorous analysis of what's going on inside the microcavity if we saturate ground state absorption. But first we extract the imaginary part of refractive index, complex refractive index from absorption spectrum of the cavity material. Then we did Kramer's chronic analysis, and then we reconstruct real part of the complex refractive index, and then we saturate absorption for 10% and see what's going on with the refractive real part of the refractive index, the red curve. You can see that on the left side of with respect to the absorption maxima, we have decrease of the refractive index. On the right hand side we can see increase. Therefore normally our polariton systems are located in here, so we have decrease of the refractive index. Therefore our cavity mode should increases, and if our cavity mode energy increases, therefore detuning decreases, and that result in blue shift of the polariton state as well. If now put all this contribution together and derive energy change for the low polariton branch as the function of dimensionless saturation parameter eta, which is basically equal to the number of excitation in systems over the whole amount of molecules, one can easily see that for the eta much less than 1, so for the small saturation parameter we can ends up with a very nice and relatively simple analytical solution for the blue shift, where the first term, the analytical solution, consists of two contributions. One is the contribution from bright molecules, which is proportional to the Rabi splitting in the system, and another one is comes from the dark molecules. This one is inverse proportional to the refractive index of dark of the cavity material, and also depends strongly on the detuning, because the tuning is also in here as a parameter d, dimensionless parameter d. And it turns out that the contribution from dark molecules to the blue shift is even stronger. It's almost 2.5 times stronger for the sample with a low concentration, because it has smaller detuning and smaller the Rabi splitting. But for 10%, it is even for 10% when the Rabi is twice stronger, approximately. Anyway, the contribution from dark molecules to the blue shift is stronger for 1.5 times approximately. It has to be stressed out that the contribution from dark molecules is very important, and they change the entire dependence of the blueshift with respect to the exciton fraction, because as you can see here, the dotted curves demonstrate the contribution from Rabi quenching. It is always increasing with increasing the exciton fraction. But what's going on with the the contribution from dark molecules, it is quite different, because it changed sign once you cross the zero detuning. Therefore, it results in non-monotonous dependence for the overall blueshift with respect to exciton fraction, with some maximum value reached at 0.2 approximately and 0.3 of exciton fraction. Then it goes down. This goes in complete different way with respect to the prediction from polariton scattering or polariton exciton scattering. Finally, we figure out why the blueshift appears in a step-like way, and it is actually omnipresent feature of the all-known crystalline organic microcavities evidenced by different groups, not only in our lab. This step-like behavior of the blueshift. So it turns out that that there are lots of different molecules with different projections of the dipole moment. Some of them are parallel to the linear polarization of the laser, some of them are perpendicular, and some of them could be even out of plane as represented in this figure. But in the in the densely packed organic films, it is very well known that there is a first resonance energy transfer between molecules, dipole-dipole, due to the dipole-dipole interaction. And this energy transfer is very fast in organic materials. In our organic system, it was shown in a group of David Lidzi that it is happening within the 30 picosecond. So if we, for instance, excite our organic material with we predominantly excite with linear polarization those molecules which are parallel which has a dipole moment line parallel with the laser, then within the 30 picosecond the polarization would be randomized over all other projections as well. It's just because they are say there is a crosstalk between different molecules, and we show that indeed below condensation we have unpolarized light, but once we have we've built our condensate state, we observe very high degree of polarization of our system, and this is accompanied with a jump-like blueshift in the system. To quantitatively describe nonlinearity of condensates, we developed a phenomenology which is based on three types of molecules: parallel, aligned parallel with linear laser polarization, perpendicular, and out of plane. And below threshold, if we excite, for instance, these molecules only, then they, due to the crosstalk, the energy transfer, they distribute population over the whole, all three types of molecules. But what's going on above threshold? Above threshold, we trigger bosonic stimulation into the polariton state, or polariton ground state. Therefore, this level, this sort of molecules, they depopulate very strongly into the polariton state, and therefore the energy transfer is not efficient enough to decrease population of these molecules. And that's why above threshold we have jump-like blueshift, because we saturate strongly these sort of molecules. But below threshold, the saturation, let's say, diluted due to the energy transfer between other sort of molecules. Finally, I would like to stress out that the contribution of weakly coupled molecules, so-called dark molecules, to the linearity of organic condensates is very strong. In our particular case, it is even stronger than for bright molecules. Therefore, I would say that effective polariton interaction models are not very good approximations for organic condensates, as it may lead to wrong predictions. Also from here, I would say that therefore blueshift cannot be considered generally as a hallmark of organic polariton lasing. And Also, I think the reservoir of coupled molecules could be used as a powerful tool to engineer polariton spectral properties, because one can also think about the redshift. So if one can play around the position of dark molecule reservoir with respect to the polariton states, it could be the energy shift, nonlinear energy shift could be engineered, I think. And finally, intermolecular energy transfer is usually present in organic microcavities, was shown in our study, and we explicitly show that it defines threshold of the condensate, its polarization and spectral properties, and we developed I think nice phenomenology to quantitatively describe these things in organic polariton. Let me acknowledge all my colleagues who contribute to this nice study, in my point of view. From Southampton, people from Sheffield, of course, from David Lidzi Group, and Skoltech. Thank you for your attention.